When you see this formula, you might be reminded of Pythagoras, a mathematician from ancient Greece. You might be reminded of right-angled triangles, and you might even have some idea of how the formula works. But do you know why it works? Just so we're all starting in the same place, I'm going to start with a short example of how Pythagoras works, before digging deeper into why it works. If you take any right-angled triangle, the square of one shorter length plus the square of the other shorter length, that's A and B, will add together to give you the square of the longer length. In this case, we've got 3 squared, which is 9, plus 4 squared, which is 16, and that gives us the square of our missing length. So 9 plus 16 is c squared, so 25 is equal to c squared, and then we can work out that the longest side must be 5. Hello and welcome back to Mr. Butler Maths. In this video, I'm going to give you a visual proof of Pythagoras' theorem. Before we can do that, let's first remind ourselves of when we can use Pythagoras. So, we can't use Pythagoras with every type of triangle. Here are 6 triangles, and we can only use Pythagoras for 3 of them. We can only use Pythagoras for the 3 right-angled triangles. I've marked those 3 right-angled triangles with a little square on the right angle. The right angle is 90 degrees. Let's just focus on those 3 triangles. Let's also just remind ourselves of some terminology. So we have a right angle, which I've marked with a square, which is 90 degrees. And then opposite the right angle, the longest side length is called the hypotenuse. And in many cases, hypotenuse is associated with the letter C from the formula that I presented. But there's no reason it has to be the letter C. You could use a different letter here. And it's also worth briefly pointing out that we can rearrange the formula to work out any missing side length of a right-angled triangle as long as we know 2 side lengths. Even if we had the hypotenuse and one other side length, we could use that to work out the missing side length, even if it's not the hypotenuse. We now know where we can use Pythagoras' theorem, and that's with right-angled triangles. But why can we use Pythagoras' theorem? And by that I mean, how can we demonstrate that Pythagoras' theorem is true? I'm going to demonstrate this using a visual proof made up of different triangles and squares. So let's start with a right-angled triangle. Let's label the sides A, B, and C. Now, if we think back to our formula, we didn't use A, B, and C. Instead, we used A squared, B squared, and C squared. One way to visualize A squared, B squared, and C squared is using squares. A square for which every side length is A will have an area of A squared. Therefore, this orange square has an area of A squared. A square for which every side length is B will have an area of B squared. Therefore, this blue square has an area of B squared. A square for which every side length is C will have an area of C squared. Therefore, this pink square has an area of C squared. So now I've given us a more visual understanding of what A squared, B squared, and C squared are. Now's a good time to think back to the theorem. The theorem tells us that A squared plus B squared is equal to C squared. What that means in terms of these squares is that the orange square plus the blue square will have the same area as the pink square. And this is what we've got to demonstrate to ourselves. So let's move our orange and blue square to one side and our pink square to the other side. We want to show that these two are equal. One way I could do this is cut up the orange square and stick it round the edges of the blue square such that the orange square plus the blue square give me the same area as the pink square. However, I'm not going to do that because I don't think that's very convincing, because it's not clear that when I cut up the orange square that I haven't made any parts bigger or smaller. Also, just because I know that these 2 squares on the left-hand side can be stuck together in a specific way to make the square on the right-hand side, doesn't mean I know this will work for every type of right-angled triangle. An advantage of the method that I'm about to show you is that it does generalize to every type of triangle, and this means it's a lot more convincing. The way that I'm going to demonstrate A squared plus B squared is equal to C squared is using a copy of my original triangle. In fact, I'm going to use several copies. Let's move this yellow triangle over to the C squared. We'll play around a little bit with the right-hand side, and then once I've done that, I can demonstrate that the pink square is equal to the orange and blue square. So I've got my yellow triangle there. I'm going to make a copy of it, and I'm going to stick that copy there. As you may be able to see, I'm starting to make another square, okay? And I'm actually going to use 4 copies of this yellow triangle to make that other square. On the right-hand side, I have c squared plus 4 triangles. Those triangles are exact copies. They all have exactly the same area as our original triangle. I'm now going to copy those 4 triangles, not changing their size or shape at all. I'm going to copy them and move them over to the left-hand side. So I've moved them over to the left-hand side, and we can see that they don't fit. But let's see what happens when I move those triangles around a little bit. Keep in mind, I'm not changing their shape or size, I'm just moving them. I'm going to move one of them up to the top right corner, and then I'm going to move the 2 together to fill the bottom left corner. So now, on the left-hand side, I've made a square out of a squared plus b squared and 4 of my original yellow triangles. That's the same number of yellow triangles as I had on the right-hand side. As you may be able to tell just by looking at it, the square that I've built up on the left-hand side has the same area as the square that I've built up on the right-hand side. But how do I know? Well, let's have a look at the area of each square. Remember, to find the area, I need to know the side lengths. So let's start with the right-hand side. The side length of this square is going to be a, which I get from the side of the original triangle, plus b, which I get from the other side of the original triangle. So one side is a plus b. In fact, it is a square. And we can see this because the other side lengths are b plus a. A plus b is equal to b plus a. Therefore, those side lengths are the same. And we've got all of those side lengths from our original triangle, which we've just made copies of. Okay, so now I know the side lengths of my right-hand square. What are my side lengths for the left-hand square? I know that that shorter side length of that original triangle is going to be a, and I know that each side length of the blue square is going to be b, because the area of it was b squared. So one side of my left-hand square is a plus b. I also know that the other side of the blue square is going to be b, for the same reason. And I also know that the shortest side length of that triangle is a. So again, I have a plus b as a side length. As you can see, the left-hand square and the right-hand square are the same size. Okay, but you might be thinking to yourself, great, Mr. Butler, you've shown that they're the same size, but how does that help us with Pythagoras again? So remember, our aim was to show that a squared plus b squared is equal to c squared. I've shown you that these 2 squares are equal. Now let's take away part of each square, one step at a time. I'm going to take away one triangle from both squares, and another triangle, and another triangle, and another triangle. And then I'm left with what I wanted at the start. I've got a squared plus b squared is equal to c squared. So you might be thinking to yourself, okay, Mr. Butler, you've shown me that this orange square plus the blue square is equal to the pink square, but what was the whole point of this anyway? Well, let's start by bringing it back to our original triangle and Pythagoras' theorem. Pythagoras' theorem tells us that a squared plus b squared is equal to c squared. And using a combination of shapes, we have demonstrated, we've proved that this is true. Proving something true is a foundational part of mathematics. Now that we've proven it's true, we know that it will apply it in any context, and we can feel much more confident in using it in all of these contexts. Now, Pythagoras' theorem was proved a long time ago, so we already have been using it very confidently. However, I still think having an idea of how to prove it for yourself deepens your understanding of Pythagoras and the way in which maths works more generally. And as an added bonus, I think it looks quite nice on the screen too. I'm going to leave it there for this video. If you have any other mathematical topics that you think would really benefit from an animated video, don't be afraid to leave a comment. I'm always on the lookout for new ideas. Thanks, guys.